Good day. For those of you who do not know me, my name is Douglas Harder. In this topic, we're going to discuss projections and best approximations. So in this topic, we will define the projection of one vector onto another. This is going to be the best approximation of that one vector as a scalar multiple of the other vector. We will first find the formula for real finite dimensional vectors and then discuss the formula for complex finite dimensional vectors. We will look at a number of examples and then some properties of the projection. We will look at the projection of functions onto functions as well, and we will discuss the average value of vectors. Now, to motivate this discussion, let's take a look at these two vectors u and v. Now, clearly u is not a great approximation to v. Yeah, they're sort of pointing in the same direction, but it's about twice as long. If you were to, however, to multiply u by 0.4, the resulting shorter vector does seem to be a better approximation of the vector v. The question is, which scalar multiple of u is the best possible approximation of v? Well, for this we need an explicit, quantifiable definition of best. So therefore, a reasonable definition is which scalar multiple of u is closest to v. And of course, closest here means distance. And the distance between two vectors, alpha times u and v, is calculated by the 2 norm of alpha u minus v. Now, recall that the function x squared is monotonic for x greater than or equal to 0. And that means that if x is less than y, that's true if and only if x squared is less than y squared. What this means is that we can minimize either the 2 norm or we can minimize the 2 norm squared. And the minimum of one will equal the minimum of the other. Thus, finding the minimum of this 2 norm of this difference is equivalent to finding the minimum of the 2 norm of this difference all squared. But the 2 norm squared is just the inner product of this difference with itself. All right, now, you know that the inner product is linear. So for example, looking at the bottom, if we had alpha times u minus v inner product with w, this is the same as taking alpha times the inner product of u and w plus -1 times the inner product of v and w, which simplifies to what you see there. Well, that's what we have here, except let us just treat the second argument as w. So in this case, we just have alpha times the inner product of u and that linear combination minus the inner product of v and that linear combination. Okay. Now, wait a second, we can do the same thing with both of these inner products, but with a second term. So, the first one expanded is just alpha times the inner product of u and itself minus the inner product of u and v. And this is, of course, all times alpha, as the inner product was previously multiplied by alpha. The same thing with the second. We are now going to subtract the inner product of alpha times the inner product of v and u minus the inner product of v with itself. All right, now let's expand that out. So the first term expanded is just alpha squared times the inner product of u and itself minus alpha times the inner product of u and v. The second term expanded is just minus alpha times the inner product of v and u plus, as the two negatives cancel, the inner product of v and itself. Okay, now you also will remember that for the inner product, it is symmetric, at least for real inner product spaces. So the inner product of u and v is equal to the inner product of v and u. So we can simplify it to this term here. All right, now let's take it from here. Therefore, this 2 norm squared is just equal to this linear combination of inner products. Now, remember that u and v are given, and so therefore the inner product of u and itself, -2 times the inner product of u and v, and the inner product with v and itself are just constants that can be calculated. So what we really have is a polynomial in alpha. So, for what value of alpha is this particular polynomial a minimum? Now, of course, to have a minimum, a polynomial must be concave up, and therefore C2 must be greater than 0. That's okay because in the above polynomial, the coefficient of alpha squared is the 2 norm squared of u, which, if u is not the 0 vector, is strictly greater than 0. Well, to find the minimum, you differentiate, equate to 0, and solve for alpha. So differentiating that quadratic with respect to alpha and equating to 0 gives us the following algebraic expression. Then solving for alpha gives us that alpha is negative the linear coefficient over twice the coefficient of alpha squared, all negated. Therefore, let's just substitute in the two coefficients. That is the coefficient of alpha and the coefficient of alpha squared. And that's equal to this expression here, where -2 times the inner product of u and v is the coefficient of alpha, and the inner product of u and itself is the coefficient of alpha squared. Now, canceling out the minus signs and the 2's, this leaves us with alpha being this ratio of inner products. Thus, the best approximation of v as a scalar multiple of u is given by this ratio of inner products times the vector u. Now, remember that an inner product returns a scalar, and the ratio of two scalars is just another scalar. So this is just a scalar multiple of u. We will denote this projection as the projection of v onto the vector u shown here. So u is fixed. We can use different v's and find different projections onto this particular vector u. Now, so for example, here are two vectors. Therefore, the projection of u onto v would be approximately this vector here. And it is called the projection because we are essentially projecting the vector perpendicularly onto the vector u. We'll take a look at that later. But let's look at some examples first. Now, just one special case. The formula we just derived assumes that u is not equal to the 0 vector. Let us define the projection of any vector onto the 0 vector as simply the 0 vector. After all, the best approximation of any vector by a multiple of the 0 vector is the 0 vector itself. Not a very good approximation, but technically correct. In general, in this course, however, we will always be projecting vectors onto non-zero vectors. All right. Now, given the vector u is 1, 1, and the vector v 3, 7, we'd like to find a scalar multiple of u that best approximates the vector 3, 7. Now, that could be any vector on the blue dotted line. Now the projection of V onto U is given by this ratio of inner products times U. And in this case, the inner product of U and V is just 1 times 3 plus 1 times 7. And the inner product of U and itself is just 1 times 1 plus 1 times 1. This is all multiplied by the vector U. Now, evaluating this, we see that this is 10 over 2, or it is equal to 5 times the vector 1, 1, which is just the vector 5, 5. Therefore, the best approximation of the vector 3, 7 as a scalar multiple of the vector 1, 1 is the vector 5, 5. Now, you can also note that the vector v is equal to 5, 5 plus the vector 2, negative 2. And you will note that the vector 2, negative 2 is orthogonal to the vector u. So the inner product of u, which is 1, 1, and 2, negative 2 is 1 times 2 plus 1 times negative 2, which is equal to 0. So the difference between v and its projection is actually orthogonal to u. Now, let's go a little bit more into detail about this. We calculated the projection of v onto u as the vector 5, 5. Let us call the error the perpendicular component of v mapped onto u. And that is just going to be the error. So that will be the vector v minus the projection, which is the vector negative 2, 2. You will notice that the projection of v onto u is perpendicular to the perpendicular component of v mapped onto u. So therefore, v is equal to the projection of v onto u plus the perpendicular component. So if I add 5, 5 onto the vector negative 2, 2, I get the vector 3, 7. Now, because the vectors are perpendicular, we can also use Pythagoras' theorem. So therefore, the 2 norm squared of the projection of v onto u plus the 2 norm squared of the perpendicular component of v mapped onto u is equal to the 2 norm squared of the vector v. And we see that this is indeed true in this case, for the 2 norm squared of the vector 5, 5 is 5 squared plus 5 squared. The 2 norm squared of the vector negative 2, 2 is just 2 squared plus 2 squared, and the 2 norm squared of the vector v is just 3 squared plus 7 squared, and 25 twice is 50 plus 8 is the same as 49 plus 9. In other words, 58. So yes, 58 does indeed equal 58. Let's go into R3 now. Let us find the projection of the vector v onto this vector u. Now, you can see that the vector v is approximately negative 2 times the vector u. So when we find the projection, we should get approximately negative 2 times the vector u to be that projection. So the projection is defined as this ratio of inner products times the vector u. In this case, the inner product is 2 times negative 4, negative 0.9 times 2, 1.2 times 2, and that is over the 2 norm squared of the vector u, which is 2 squared plus 0.9 squared plus 1.2 squared. All of this is multiplied by the vector u. Now, this works out to this value here, and that ratio equals negative 1.952. So when we multiply the vector u by that scalar, we get this vector here, which, yes, is reasonably close to the vector v. As you can see, the vector v is not a scalar multiple of u, but it's pretty close to negative 2 times the vector u. Now, notice that the vector v is indeed equal to this vector here plus the perpendicular component. So those two vectors added together give the vector v, and remember that the vector u, or any scalar multiple thereof, and the perpendicular component are orthogonal, and therefore the inner products of these must be 0. So for example, 2 times negative 0.096 plus negative 0.9 times 0.2432 plus negative 1.2 times negative 0.3424 does indeed exactly equal 0. Now here's one final example in R4. Let us find the projection of the vector on the right, v, onto the vector u seen here. Again, we just use the definition of the projection. So we calculate the inner product of u and v, and divide that by the inner product of u and itself. This gives the ratio 20 over 6.25, and that works out to 3.2. So if we multiply the vector u by 3.2, we get this vector here. Now, this vector isn't as close as the previous vector, but again, note it's reasonably close. 1.92 is sort of close to 3. Negative 5.76 is close to negative 5. 3.84 is close to 4, and negative 3.52 is close to negative 4. It's a little bit further away than the previous example, but that's okay. Because again, v is equal to this projection plus the perpendicular component. And if you were to calculate the inner product of these two vectors, you would find that they are, yes, indeed, orthogonal to each other. Any other scalar multiple of u will be further away from v than the vector that we just calculated. Now, in finding the projection for real inner product spaces, we use the symmetry of the inner product. That is, the inner product of u and v equals the inner product of v and u. In complex vector spaces, this is not necessarily true. The inner product is conjugate symmetric. That is, the inner product of u and v is equal to the conjugate of the inner product of v and u. Consequently, the derivation of the projection, that is, the best approximation, is a little bit more complex. This is done in the textbook, and it turns out to be the same formula. It's important here, however, that the v is in the second operand of the inner product in the numerator. Now let's talk about properties of projections. First of all, a function f is said to be idempotent if, after having applied f to x, if you apply f one more time, it leaves the result unchanged. And this must be true for all arguments x. That is, once the function is applied, subsequent applications of that function do not affect the result. Now, you may wonder, what are these functions useful for? What are they? Well, actually, you've already seen a number of different idempotent functions. For example, the absolute value function is idempotent. The absolute value of the absolute value of x is the absolute value of x. Taking the absolute value is a positive real number, and taking the absolute value of a positive real number leaves that number unchanged. Also the ceiling function, or the least integer that is greater than or equal to x. So for example, the ceiling function of 3.7 is 4, but the ceiling of 4 is still 4 and therefore unchanged. Similarly, the floor function, or the greatest integer less than or equal to x, is also idempotent. The floor of 7.82 is 7. And if you calculate the floor of 7 again, you get 7, for 7 is indeed the greatest integer less than or equal to 7. So you've already seen 3 explicit idempotent functions. You just may not have realized this property. So theorem: the projection is idempotent. That is, the projection of V onto U is equal to the projection of that result again onto U. Proof: well, the projection of V onto U is given by this ratio of scalars times the vector U. Therefore, the projection of this projection onto U is just substituting this argument into the second operand of the inner product in the numerator. All right, but wait a second. In the numerator, we now have the inner product of U and a scalar times U. But wait a second. Remember that value is a scalar, and if we had the inner product of U and alpha times V, then the alpha can come out, and the alpha can come out whether or not it is a real vector space or a complex vector space. So what that means is the ratio of those two inner products is a scalar that can come out of the inner product in the numerator. Let's take it out. All right, there we have it. But wait a second. Now take a look at the denominator of the ratio in the numerator. That's equal to the inner product of U and V. So those two terms cancel out. So we're just left with the inner product of U and V over the inner product of U and itself times the vector U. But that is the projection of V onto U. All right. So therefore, projecting the projection onto U does not change that projection. Therefore, the projection is idempotent. Now, a function f is said to be linear if f of a linear combination of vectors is equal to that same linear combination of f applied to each of those vectors for all possible scalars alpha, beta, U, and V. So here's an example of a linear function. F is simply going to multiply the vector U, the argument, by 3. Note that f applied to this linear combination of vectors is equal to 3 times that linear combination. By the distributive property, it's equal to that. By the associative property of field multiplication and scalar multiplication, that is equal to that expression. And, oh, wait a second. This is just 2 times the function f applied to U plus 5 times the function f applied to V. So this is one simple example of a linear function. Now, more useful, however, is the derivative. The derivative is linear, and you already know this. However, you may not have described it as such. So the derivative of a linear combination of functions f and g, well, that's just the derivative of a sum, and the derivative of a sum is the sum of the derivatives. Oh, but wait a second. The first is just the derivative of alpha times f, which is equal to alpha times the derivative of f, and the second is the derivative of beta times g, which is just equal to beta times the derivative of g. So therefore, the derivative of a linear combination of functions is equal to that same linear combination of the derivative of those functions. For example, if you were to calculate the derivative of 3 cos plus 5 times sine, that's just equal to the derivative of 3 times cos plus the derivative of 5 times sine, which is just 3 times the derivative of cos plus 5 times the derivative of sine. But the derivative of cos is negative sine and the derivative of sine is cos, so that is equal to that expression there. Theorem: the projection is linear. Proof: well, the projection of this linear combination of vectors v1 and v2 is just the inner product of u and this linear combination over the inner product of u and itself, all times the vector u. But wait a second, the inner product is linear in the second operand for both real and complex vector spaces. And so therefore the numerator can be expanded into this linear combination of inner products. Now, using the properties of field multiplication and scalar multiplication, we can rewrite this as the following expression. But wait a second, alpha 1 is being multiplied by that ratio times u. But that ratio times u is just the projection of v1 onto u. Similarly, the second term is alpha 2 times the projection of v2 onto u. So therefore, the projection of a linear combination of vectors onto u is equal to that same linear combination of projections of those vectors onto the vector u. What this means is, given a linear combination, such as alpha 1 times v1 plus alpha 2 times v2, you can either calculate that linear combination first and then calculate the projection, or you can calculate both the projection of v1 onto u and the projection of v2 onto u, and then calculate the linear combination of those two projections. Theorem: the 2 norm of the projection of v onto u is less than or equal to the 2 norm of v. What that says is that if v is ever projected onto any other vector, the 2 norm or length of that projection must be less than or equal to the length or 2 norm of v. Also, these 2 norms are equal if and only if v is equal to alpha times u. And if v is indeed equal to alpha times u, that is the same as saying that the projection of v onto u is equal to v. Because after all, v itself is the closest scalar multiple of u, in this case, to v. Anyway, let's prove this theorem. So, to prove this, observe that v is equal to the projection of v onto u plus the perpendicular component of v projected onto u. Now, the projection and the perpendicular components are perpendicular to each other. And so that means we can apply the Pythagorean theorem. So the 2 norms squared of the projection plus the 2 norms squared of the perpendicular component must be equal to the 2 norm of v all squared. Now, all 3 of these terms are non-negative, so if a non-negative number is equal to the sum of 2 other non-negative numbers, that means that if I remove one of them from the left-hand side, what's left must be less than or equal to the right-hand side. 3 plus 4 is equal to 7. Therefore, 3 is less than or equal to 7, and 4 is less than or equal to 7. All right, nice. But wait a second. The square root function is strictly monotonic for all values of x greater than or equal to 0, and therefore, if the 2 norm squared of the projection is less than or equal to the 2 norm squared of v, that means that the 2 norm of the projection of v onto u is less than or equal to the projection of v, the 2 norm of v. Let's prove the other part of this. Assume that these two norms are equal. Well, if these 2 norms are equal, then the squares of each of these are equal. But wait a second, if we go back to the Pythagorean theorem, that means that the 2 norm of the perpendicular component is equal to 0, and if the 2 norm of a vector is 0, that means that that vector itself is equal to 0, and therefore the projection of u onto v onto u plus the 0 vector is equal to v, and therefore v is equal to the projection of v onto u, and therefore the projection must be a scalar multiple of u. Let's prove the alternative. Assume that v is equal to alpha times u. Well, therefore, the projection of v onto u is just the projection of alpha u onto u. But alpha is a scalar, and we just proved that the projection is linear. So we can actually just take that alpha out of the projection, leaving us with the projection of u onto u. Well, wait a second, that's just that, and the numerator and denominator cancel, they're equal, and so that's just equal to alpha times u, which is equal to v. Therefore, we're finished. Next theorem. If u cap is a unit vector, then the projection of v onto that unit vector is just equal to the inner product of v and that unit vector multiplied by the unit vector. Basically, what this means is we can do the calculation with one fewer inner products. Proof. Well, this is by definition the projection of v onto u cap, but the inner product of u cap and itself is equal to the 2 norm squared of u cap. And if u cap is indeed a unit vector, then the 2 norm of u cap must be equal to 1. Therefore, the 2 norm squared is also equal to 1. And therefore, the projection is just equal to that particular inner product over 1, which is just the inner product we see above times u cap. So once again, this tells us that if the vector u is a unit vector, then we can reduce our work by approximately half. Now, here's another theorem. The projection of v onto u is equal to the 0 vector if and only if u and v are orthogonal. That is, their inner product is equal to 0. Proof. Now, if u is equal to the 0 vector, then the projection of v onto u is the 0 vector, and every vector is perpendicular to the 0 vector, for the inner product of any vector and the 0 vector is 0. All right, that's the easy part. Let us assume that u is not equal to the 0 vector. Well, if u is not equal to the 0 vector and the projection of v onto u is the 0 vector, that is true if and only if this ratio times the vector u is equal to the 0 vector. Now, the vector u is not the 0 vector by assumption, So therefore the ratio must be 0 for this to be true, and because the ratio is 0 if and only if the numerator is 0, then this is true if and only if the inner product of u and v is equal to 0. That is, u and v are orthogonal, or those two vectors are perpendicular to each other. What that says is that if the vector u is perpendicular to the vector v, then the best approximation of v as a scalar multiple of u is the 0 vector. That is, there is no information in the u vector that could possibly approximate or give any information about the vector v. Now we're going to look at projections in other vector spaces. However, you are not responsible for evaluating these on any examination. Let us find the best scalar multiple of the polynomial x that approximates the sine function on the interval from -1 to 1. All right. Now, y equals x is actually a very good approximation of the sine function close to x equals 0, as we can see in this image where the sine function is in red and the function y equals x is in black. However, notice that as we get further and further away from 0, the approximation becomes worse and worse. Is there a better scalar multiple of the function y equals x that could provide a better approximation of sine of x over the entire interval? Well, we want to avoid that large error close to the boundaries, so let's calculate the projection. Now, the projection of sine onto the function y equals x is just the inner product of x and sine over the inner product of x and itself multiplied by the function x. Now wait a second. The inner product for functions is just the integral. All right. So the integral from -1 to 1 of x times sine of x is the numerator, and the integral from -1 to 1 of x times x, or x squared, is the denominator. This is all times the function x. All right, now in your calculus course, you will learn how to evaluate these integrals. So evaluating this, the numerator just works out to twice sine of 1 minus twice cosine of 1 all over 2/3 times the function x. So if we evaluate this ratio and approximate it as a floating point number, we get that this is approximately the polynomial 0.9035 times x. Okay, so in the left-hand image, we have the function y equals x. In the right-hand image, we have the function 0.9035 times x. Now, as you can see, it gives a worse approximation closer to 0, but not that bad, but it gives a significantly better approximation closer to x equals 1 and x equals -1. So this is in fact the best approximation of the sine function by a scalar multiple of y equals x on the interval from -1 to 1. Now, let us find the constant function that best approximates the sine function on the interval from -1 to 1. Now, every constant function is a multiple of the function y is equal to 1. That is the function represented by 1 with a cap over it. This 1 with a cap over it is the function that evaluates to 1 at every single value of x. That function is different from the scalar 1. Anyway, the projection of sine onto the one function is just the inner product of sine with that one function over the inner product of the one function and itself, all times the one function. Well, that's just equal to the inner product, or the integral, from -1 to 1 of 1 times sine of x dx over the integral from -1 to 1 of 1 squared dx. Now, the denominator you're going to find is equal to 2, but the numerator is equal to 0. And 0 times the one function is the 0 function. Consequently, the best constant function that can approximate the sine function from -1 to 1 is the 0 function. If you were to have a constant function that was either slightly positive or slightly negative, it would be a worse approximation. Why? Because the sine function, as you may realize, is an odd function, and therefore whatever it is for x greater than 0, its value is exactly equal to the negative of that for negative values of x. Now, if we denote the one vector by a bold 1, that is the vector in r to the n or c to the n of all 1s, then the best approximation of any vector as a scalar multiple of this one vector is the average value of the entries. Now, we can see this as follows. The inner product of the one vector and any other vector is just the sum of the entries of the other vector. Similarly, the inner product of the one vector in itself is just the sum of 1 n times, which is equal to n. Therefore, the projection of any vector onto the one vector is just the sum of the entries over n, which is the average value of the entries of the vector. And this is all multiplied by the one vector. Now, notice that all vectors that are orthogonal to the one vector are all those vectors, the sum of the entries of which is equal to 0. That is, all vectors that have an average value of 0. Now, return back to the previous question of the sine function. Is not the average value of the sine function on the interval from -1 to 1 equal to 0? In your calculus course, you will actually define the average value of a function, and you will be able to calculate it. So the same applies in finite dimensional vectors. Now notice, for functions, if you want the function that evaluates to 1 everywhere, that function is denoted by a 1 with a cap over it. If you want a vector, a finite dimensional vector that is 1 in each of the entries, we denote that as a bold 1. So just a subtle difference in representation. Consequently, following this discussion, you now know the formula for the projection of one vector onto another. You understand that the projection is the best approximation of one vector by a scalar multiple of another. You know that the projection is idempotent and linear. You also know that the 2 norm of the projection of v onto any other vector is always less than or equal to the 2 norm of v. You know that the formula for the projection onto u simplifies if u is a unit vector, as the denominator is no longer required. Also, the projection of v onto u is the 0 vector if and only if u and v are perpendicular. You've also seen the projection of functions and other interesting results. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!